MOSFETs are transistors, semiconductor electronic devices, active devices. They are widely used in the design of digital logic circuits. There exist two types in these devices, NMOS and PMOS. NMOS refers to N-channel MOSFETs. PMOS refers to P-channel MOSFETs. In these devices, source and drain both are made with the same type of material, either P-type or N-type. If they are made with P-type material, then the MOSFET is called P-channel MOSFET or PMOS. If they are made with N-type material, then the MOSFET is called N-channel MOSFET or NMOS. Another classification is also there. It also divides MOSFETs into two, DMOS and EMOS. DMOS refers to depletion MOSFET and EMOS refers to enhancement MOSFET. In DMOS, there exists a diffused channel, and as a result, these MOSFETs can be operated in two modes, either in depletion mode or in enhancement mode. In EMOSFETs, diffused channel is absent. For this reason, they can be operated only in one mode, that is enhancement mode. MOSFETs can be operated in one of two regions. One region is called triode region or linear current region. In this region, MOSFET acts as a resistor. Another region is also there. It is called saturation region or constant current region. When the FET is in saturation region, it becomes capable of providing a gain. Hence, if one wants MOSFET to act as an amplifying device, it must be biased, it must be operated in constant current region. There are three configurations as far as these devices are concerned. They are CS, that is common source configuration, CD, that is common drain configuration, and CG, common gate configuration. In the CS configuration, source is common for input and output. In common drain configuration, drain is common to input and output. In common gate configuration, it is the gate that is common to input and output. Out of the three, CS is considered to be the most versatile configuration, giving most of the desired performance in several applications. Field effector transistors, MOSFETs, part 2, series on semiconductor devices and circuits, lecture number 4.13. This is the second part of presentation on MOSFETs. In the first part, the focus has been mainly on introduction to MOSFETs, their structure, circuit symbols, and current voltage characteristics. static characteristics of MOSFETs. In this session, second part of presentation on MOSFETs, the focus is mainly on configurations, MOSFET configurations, and biasing circuits used with the MOSFETs. We also cover certain analytical expressions which describe current voltage characteristics of MOSFETs. Let us start the session with a few points on current voltage characteristic of MOSFETs. Basically, there exists two regions in the current voltage characteristic of MOSFETs. One is linear current region or constant resistance region. This region is also called a triode region. Another region is there, saturation region or constant current region. Both the regions are described in an official way in this slide. Triode region. When VDS, voltage of drain with respect to source, when it is less than or equal to VGS minus VT. VGS is voltage of gate with respect to source. VT is threshold voltage, which was already introduced. When VDS is less than or equal to VGS minus VT, the device is said to be operating in a triode region. Here, the drain current is a parabolic function of VDS, drain to source voltage. Deep triode region, when VDS is very much smaller than VGS minus VT, the device is said to be operating in a deep triode region. Here the drain current is a linear function of VDS. The path from the source to drain can be represented by a linear resistor. Thus, a MOSFET can be operated as a resistor. It can be used as a resistor whose value can be controlled by the overdrive voltage provided. Of course, VDS is very, very small when compared to VGS minus VT. The point is this. This is ID, this is VDS. Near the origin, characteristic is like this. This is a deep triode region. Later, triode region comes into being. Much later, saturation region or constant current region. So, triode region, deep triode region. First deep triode region, then triode region. Usually together these two are referred as a triode region. The voltage VGS minus VT is called overdrive voltage. This quantity, this quantity, this quantity, it is overdrive voltage, and W to L ratio is called aspect ratio. Here L is dimension of gate along source drain path and W is its width. A few points regarding saturation region. When the drain to source voltage exceeds the overdrive voltage, that is VDS is more than VGS minus VT, then the drain current no more follows a parabolic path. In reality, the drain current becomes relatively constant. That's why this region is called constant current region, as already mentioned. And the device is said to be operating in saturation region. MOSFETs start acting as a current sources in this region. It has been already mentioned that MOSFET requires to be saturation region or constant current region if we want it to function as an amplifier. Not only that, if we want MOSFET to act as a current source, then we have to operate it in same region, saturation region. Certain relations are given here under MOSFET physics. NMOS. These relations are for NMOS. Overdrive voltage is VOE. It is VGS minus VT as already mentioned. Therefore, VGS is VT plus VOV. Operation in triode region conditions are VGS more than or equal to VT. It gives overdrive voltage more than or equal to 0. VGD should be more than or equal to VT. It gives VDS is less than or equal to VGS minus VT. It gives VDS is less than or equal to overdrive voltage. So these are conditions when we want the device in triode region to be satisfied. IB characteristic. ID drain current is mu n C naught x W by L VGS minus VT VDS minus half VD square. Mu n stands for mobility of electrons. This is C naught x is capacitance per unit area. WL are already described. VGS, VT, VDS, all those things are already explained. So this is VI characteristic. When VDS is much smaller than 2, VGS minus VT leads to VDS is smaller than 2 overdrive voltage, VOE. RDS, it is the resistance. It is by definition VDS by ID. It is a small v, it is a small I, therefore it is a dynamic resistance, small signal resistance of the MOSFET when it is working in triode region. It has certain importance. It becomes equal to 1 over mu n C naught x W by L VGS minus VT multiplied by VDS. This is the expression for RDS. So this particular part pertains to triode region behavior of MOSFET. Now we consider saturation region. Conditions for MOSFET to be fulfilled when it wants to be in saturation region. They are VGS must be more than or equal to VT minus VT. That is, overdrive voltage should be more than or equal to 0. VGD should be less than or equal to VT. It implies VDS should be more than or equal to VGS minus VT. It leads to VDS is more than or equal to overdrive voltage, VOV. Current voltage characteristic. It is given by ID equal to half mu n C naught x W by L VGS minus VT whole square 1 plus lambda VDS. The symbols, the letters that are there in this expression, they carry their usual meanings. Process parameter. C naught x is capacitance per unit area. It is epsilon naught x by T naught x. K prime n is mu n C naught x. V prime A is early voltage. VA is early voltage. VA by L is defined as V prime A. Lambda is 1 by VA. Gamma is square root of TQNA sigma S by C naught x. Previous slide it is NMOS. Now in this slide we consider PMOS. Overdrive voltage is VO is VGS minus VT. It leads VSG is equal to mod VT plus mod VOV. When it is working in the triode region, it satisfies conditions. What are those conditions? VGS is less than or equal to VT. It means overdrive voltage V0V is less than or equal to 0. It gives VSG is more than or equal to mod VT. VDG is more than or equal to mod VT. It gives VDS is more than or equal to VGS minus VT. It leads to VSD is less than or equal to mod VOV, overdrive voltage. This is when the MOSFET is in a triode region. When it is in the saturation region, conditions to be satisfied are VGS is less than or equal to VT, implies VOV, overdrive voltage is less than or equal to 0. It leads to VSG more than or equal to mod VT. VDG is less than or equal to mod Vt, it leads to Vds less than or equal to Vgs minus Vt. It gives rise to Vsd more than or equal to mod overdrive voltage. Here only conditions are given. Conditions to be satisfied in triode region, conditions to be satisfied in saturation region. When it comes to IV characteristics, these are same as NMOS transistor, except N and A is to be replaced by P and D in subscripts, and Vt, Vt naught, Va, lambda, gamma are negative. Now a few points regarding transfer characteristic. In case of MOSFETs, depletion MOSFETs, the transfer characteristic is given by IDS is equal to IDSS multiplied by 1 minus VGS over VGS of whole square, where VGS of called gate source cutoff voltage or pinch off voltage Vp is gate voltage at which ID is reduced to some specified negligible value at recommended VDS. About pinch off voltage, a discussion has already been carried out in the first part on MOSFETs. Here the focus is on transfer characteristic. IDSS has also been covered in the first part of the presentation. Note that the parabolic expression between parabolic relation between IDS and VGS. This is IDS, this is VGS, called Shockley's equation, have been derived from an experimental graph for transfer characteristic. Basic point is it is an experimental graph derived expression, not a theoretical one. In case of MOSFETs, it is given by IDS is K VGS minus VT whole square. So first relation is for DMOS, second one is for EMOS. Here in this slide, different modes are shown. There are 4 modes of operation for MOSFETs. A and B are enhancement type, normally off. C and D are depletion type, normally on modes. In A, it is NMOS. In B, it is PMOS. In C, it is NMOS. In D, it is PMOS. A and B are MOSFETs because there is no diffusion channel. Diffusion channel is absent in A and B. Therefore, it is these two are enhancement type. In the C and D, you can find diffusion channel. Diffusion channel. So therefore, these two are D type MOSFETs. A little bit of description is given regarding modes of MOSFETs. N-channel enhancement mode, normally off. When the gate voltage is 0, the channel conductance is very low and it does not allow the charge to flow. A positive voltage must be applied to the gate to form an N-channel for conduction, thus enhancing the drain current. N-channel depletion mode, normally on. Depletion mode means on, normally on. Enhancement means normally off. If an N-channel exists at 0 bias, a negative gate voltage must be applied to deplete the carriers in the channel. In effect, the channel conductance is reduced and the device is turned off. P-channel enhancement mode. Enhancement means normally off. Why it is normally off means when there is no gate voltage, no conductivity in the channel and no current flows between source and drain. So it is no current means off. When current is there, it is on. A negative voltage must be applied to the gate to induce a P channel for conduction. P channel depletion mode. It is normally on. Why it is normally on? No gate voltage is required to flow current. That's why normally on. A positive voltage must be applied to deplete the carriers in the P channel for non-conduction. This particular slide describes the functioning, the working of four structures that are shown in the previous slide. Now we move to FET configurations. The FETs can be operated in one of three configurations, namely CS, CD, CG. CS stands for common source, CD stands for common drain, and CG stands for common gate. The point here to be noted is FET is usually a three-terminal device. To give input, two terminals are required. To take output, two terminals are required. And as there are only three terminals, one terminal must be common for both input and output. The configuration that results is then named after common terminal. If source is common for input and output, then the configuration, the resultant one, is called common source. Similar is the case with the CD and CG. CS configuration amplifier is characterized by these properties. It has a voltage gain. It exhibits 180 degrees phase shift between input and output. It exhibits high input impedance. It exhibits high output impedance. Before going further, it requires to be mentioned here that FET configurations, this aspect refers to amplifiers, FET amplifiers. When it comes to amplifiers, FET amplifiers, one has to keep in mind that the FET has to be biased in such a way that it is working in constant current region or saturation region. This is first point. Second point is, after biasing, after properly establishing the operating point in the constant current region, then we have to connect the signal source to the MOSFET, and load also requires to be connected to the FET. Input connection requires two terminals, output connection also requires two terminals. Four terminals are required, but FET is three-terminal device, so one terminal becomes common. In case of CS amplifier, source is common. This amplifier exhibits the properties that are given here. In case of CD, drain is common between input and output. The voltage gain of this configuration is approximately equal to 1. No phase shift between input and output. Very high input impedance, low output impedance. These are important properties of CD FET amplifiers. Because of its high input and low output impedances and unity gain, CD circuit is usually used as a buffer amplifier between high impedance signal source and a low impedance load. Now we consider third configuration, CG, common gate configuration. Here gate is common. There exists no phase shift between input and output as far as this configuration is concerned. Here are shown diagrams of FET amplifiers. In A is CS configuration, in B is CD configuration, in C is shown CG configuration. CS source is common. Notice in CD, D is common for input and output. In CG, gate is common. Input is connected on the left side, output on the right side in all the three configurations. VDD, VGG, they are selected in such a way that MOSFET is in saturation region. Now a few points regarding FET biasing. Here are shown DMOS biasing circuits. Different names are there. A. In A is zero gate bias. In B is source self bias. In C is positive bias. And D is voltage divider bias. The bias which you can find in D is considered to be the most versatile, voltage divider bias. It is this which is widely used. Not only here. In biasing of BJTs also it is used. Zero gate bias, source self bias, positive bias, voltage divider bias. These are all meant for a DMOS. Notice a brief description of the circuits that are shown in the previous slide are meant for DMOS. As already told, their description is given here. In zero gate bias or fixed bias circuit, the FET gate terminal is connected to a zero bias voltage via a resistor, as the gate current is nil, producing no drop across the resistor. Gate source voltage remains fixed. The gate voltage, however, sets a value of drain current and the FET depending upon the device characteristics. This is a brief description of the functioning of zero gate bias or fixed bias circuit. In a source self bias circuit, the voltage drop across the resistor, which is in series with the device source terminal, provides the gate source bias. The drain current determines gate source voltage, which in turn sets the drain current level. It implies the existence of a feedback effect, which results in minimization of the drain current variations with the change in a device or its characteristics. Now, a few points on drain feedback or positive bias circuit. This circuit is essentially a voltage divider bias circuit, of course, with one difference. The gate voltage here is derived from drain voltage using a resistance divider network consisting of two resistors R1 and R2. The voltage drop across the source resistance helps in stabilizing the circuit, as in other voltage divider bias circuits. Voltage drop across the drain resistance also assists in stabilizing the drain current by providing a feedback path. This gives a brief description of the functioning of positive bias or drain feedback bias. Next, we move to the most versatile bias, voltage divider bias. In this, the gate bias voltage is derived by means of a voltage divider from supply. Voltage drop across the source resistor increases if drain current increases, producing more negative gate source voltage, which brings the drain current back towards its original value. Here, the circuits which are given in the previous slides, they are compared, bias circuits are compared here with respect to the accuracy in regard to the prediction of operating point. When compared to gate bias, self-bias gives better predictable biasing conditions. However, voltage divider bias circuit gives the most predictable bias conditions compared to other two. Because of its better performance conditions, voltage divider bias circuit is a highly preferred and widely used biasing method. Here the point to be noted is that predictability of the performance is a must. Predictable facility is given more by voltage divider bias circuit. Not only that, it gives better performance. Hence, voltage divider bias is used widely. Now is given a bias circuit for EMOS. EMOS drain to gate bias circuit, and in B is given its improved version. Here is some resistor RF connecting drain with gate. Here two resistors are used, R1, R2, for biasing purposes. A description of the circuit is given here. For DMOS biasing, zero gate bias, positive bias, self bias, voltage divider bias circuits are used. The positive bias circuit and voltage divider bias circuits are also used for biasing the EMOS. The source self-bias technique cannot be used for MOSFETs because the voltage drop across the RS is in a direction to reverse bias the gate, but the requirement is a forward gate bias. However, the circuit that is uniquely suitable for EMOS biasing is the drain to gate bias circuit. Consists of a drain resistor and a resistor connecting drain and gate. With this, we come to an end to the session, which is the second part on presentation of MOSFETs. In this session, the focus is mainly on configurations, biasing methods, along with few relations, current voltage relations of MOSFETs. Hope this session is useful to you. We meet again in another session with a new topic soon.